Live. Good evening, everybody, and welcome to the November Astro Talk. A little bit of housekeeping before we get into the talk. Just wanted to let everybody know that thank all the volunteers for Sea Lake Astro Fest. It went off with a bang. Thank you to Sarah, who is here to speak tonight, for coming along to that too. It was a wonderful weekend. Also, Christmas barbecue tickets for members and the public are available. For members, there has been a link emailed through. It's also in the members area of the website. And for the public, the ticketing link will be on our Facebook page and on the front page of the ASV website. So the tickets are available for that. That's November 30th. And also just letting everyone know that the Mount Buller Starfest will be happening over the weekend of the 3rd and 4th of January, which should be fun, up at the Alberg Hotel. Now, tonight's talk, Spooky Space Science by Dr. Sara Webb. Dr. Sara Webb is one of Australia's leading science communicators, working with national and international media stations on hundreds of stories a year, sharing the wonder of astronomy and space science to all audiences. I should write my notes better. Her social media explainer videos reach tens of millions of people a year, including me. I watch all of them. They're great. They're very entertaining, energetic, engaging. It's the way science outreach should be. She's also leads Australia's longest-running student-designed International Space Station experiment program, inspiring the next generation of space explorers, is a lecturer at Swinburne University of Technology. Dr. Webb researches the universe's fastest explosions, fast radio burst, FRBs. I know more than I should know about those. I've seen all that work happen, what's involved in it. It's pretty impressive. Today, Dr. Sara Webb will be talking about spooky space science. So I'm going to welcome to the stage Dr. Sara Webb. And while Sarah comes up, I will just like to say that in the spirit of reconciliation, the Astronomical Society of Victoria acknowledges the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respect to their elders, past and present, and extend that respect to all Aboriginal and Torres Strait Islander people today. Sarah, the floor is yours.
Thank you. Okay, excellent. Hello. Hi, everyone. Thank you for coming and thank you for joining online. I think I've clocked the camera over there, so I'll look at you as well. So I'm super excited to talk to you about spooky space science. Am I blocking myself? I am. This is my bread and butter. It is my favorite thing to do, both in my research, is to try and find exploding stars, merging black holes, and any EM signatures with them. But also to talk about, because I feel like the things that go bump in the night in the universe are the things that are the most magical to the general public. And that's really important when you're trying to not only inspire people to have curiosity and awe about the universe, but also inspire the next generation of scientists, especially young scientists as well. And astronomy is the perfect place to kind of pull people in. Is my mic cutting in and out? A little bit? Is it okay? Excellent. You just... Oh, okay. I will try not be as animated. Okay. Can I? Is that okay?
I always say it's not an ASV event if there's no technical issues, and I stand by that. We'll get there. It's because we're doing it on a Monday night and not a Wednesday night. That's why.
Thank you. Sorry, I thought I could be Britney Spears with the head microphone. I couldn't, and that's okay. So before I begin, I do want to acknowledge the traditional owners of the land which I live and work, and I believe also the custodians of this land which we're on tonight, though correct me if I'm wrong, and that is the Wurundjeri people of the Kulin Nation. And I think just generally as an astronomer, it's really important to acknowledge that our first astronomers in the world, who have songlines and stories verbally and orally for thousands and thousands of years, were our Indigenous Australians. And there's a lot that we can learn from them and some wonderful resources to learn about that history. Okay, so my name is Sarah. You can follow me on any of these platforms here if you are interested in social media, but I want to take you back to young Sarah before we dive into cosmic catastrophes. So what is a cosmic catastrophe? You've probably heard this word or this phrase used quite a bit, and it is alliteration at its finest. It sounds fantastic, but it also is very descriptive. It's anything that goes bang in the universe, anything that explodes, anything that flares, anything that's unexpected and energetic. And I think, as I said, this is my favorite thing to study and to share. And ultimately, it's because I have a morbid fascination of how will the world end, astrophysically speaking. I think there's 1,000 ways the world could end, non-astrophysically speaking, but how will it end based in the universe? And I think that's a question that we've probably all asked ourselves. Who've asked yourself that question? Has it kept you up at night? Yeah, maybe you're better than me if it hasn't. I've literally had sleepless nights just pondering all of the ways that the world, the universe could surprise us. And it started from an extremely young age. So I want you to meet young Sarah. This is me when I was about 5 or 6 years old. I just started school. As you can tell, I was a huge fan of Star Wars and sci-fi in general from a very young age. And I was always asking the big questions, always. My parents were probably exhausted, to be honest, because I kept asking them, what is the universe? And like staring them dead in their eyes and like begging them to tell me as a 5-year-old. They didn't know. Nobody knows. Where does it end? Like, where does the universe end? Where does the world end? Again, too much for 7 a.m. in the morning. Another favorite of mine, and something I still ponder often, is what was there before there was the universe, right? We have time and time is finite. It's not infinite. It had to begin. What was there? And I was always fascinated by that. I also wondered, would a black hole eat us? Like, very seriously, would it eat us? And if it did, what would happen if we fell into it? And will we end up like the dinosaurs? This was a big question. I think one that we probably still ask ourselves. And you can imagine, as a young Sarah, nobody had answers to those questions. And now as an older Sarah, we still don't have answers to the majority of these questions, which makes me anxious, and that's okay. But I am going to dive into a few of them because I never stopped asking questions. In my research, in my outreach, all of it kind of culminated to me combining it into my new book that came out just a week and a half ago. It's called The Little Book of Cosmic Catastrophes, and I'll talk more on it at the end. But it literally goes through and thinks about all of the things that could, in theory, happen in the universe that would somehow affect life on Earth. And it goes through all 3 stages. So what could have happened before the Earth actually formed? There is a significant amount of history in the universe that happens before our Earth even became habitable, and a lot of things that could have gone wrong. What could still happen? We are kind of a young planet, 4.5 billion years old, and we've probably got another 4 to 5 billion years until our sun dies, which I will touch on in this talk. But there's a lot that could still happen, including ourselves. I don't mention that because I find that too terrifying, but the universe could surprise us. And then, of course, what will happen? Because our sun will die, our galaxy will merge. There's things that are going to happen whether we want them to or not, but it's fascinating because it's a cycle of the universe and the fact that nothing is forever, nothing is infinite. And the universe is always evolving and changing. And I think it's kind of poetically beautiful. And I know I just said I'm anxious before. I'm actually not. I'm really not. Because when I think about all of this in our position of the universe and the fact that we exist and live in this world, it kind of is very humbling, and it makes you really appreciate just the fact that we are alive on this space rock. Okay. So before I dive into all of the ways that could end the Earth, universally / astrophysically speaking, I want to kind of define and remind you guys why the Earth is such a special, special place. Okay, so our Earth, she's stunningly beautiful. It's a rocky planet, not too far from the sun, not too close to the sun. It's just right. One thing that makes the Earth habitable, extremely habitable for life like us, is water. Water is this perfect solvent for chemical reactions, and really we are just a big walking vessel of chemical reactions happening constantly. And if we didn't have water, none of that would happen. We know that every bit of life that you find on the Earth relies on water to some degree, and this is carbon-based life, which is what we are. And we know that everywhere you go around the world where there is water, you will eventually find life. Maybe not big life, but microbial, microscopic life. And it's abundant. It's incredible. We think that without water, life might not have formed. Actually, we don't think. It's pretty certain. Based on the chemical biology that happens, water was really that first environment where the single-celled microscopic life was forming. And it was forming an insane amount of time ago, and it's taken a ridiculous amount of evolution to get where we are today, and it's just fascinating. So before water, we have two theories. Either our Earth never had water when it was first born, and it was bombarded at some point with comets and asteroids that had these water molecules. We call this period the heavy bombardment period, and it would explain how we got some of our water, but not all of it. And we're still quite confused about how was the Earth actually formed when it was condensing all of this leftover material from our sun really forming. The other theory is that maybe our Earth was born semi-wet. Maybe there was some water that was able to be condensated and collected as the Earth was kind of condensing and forming together, and then heavy bombardment brought more of it. What's interesting, though, is that if you look at every other planet, we'll ignore alien moons for now, but every other planet, rocky planet, you don't see water. You don't see it on Mercury or Venus or Mars. And the reason for that is a couple of different ones. One is that we happen to be in a place called the habitable zone, where water can exist in all three states: gas, liquid, ice. It's fantastic. Without it, it would not be very fun for us. We also have a beautiful big magnetic field, relatively weak compared to some magnetic fields in the universe, but it's there, and it protects us from solar radiation very, very well. We think Mars probably did have water, and I dive into this more in the book. The fact that Mars was probably actually very, very similar to us for a very short period of time. Likely had water, it likely had a magnetic field, it likely had an atmosphere. And then it all come crashing down because Mars's core cooled just enough that that dynamo action wasn't happening, and the magnetic field essentially turned itself off. We are extremely lucky that our magnetic field is still here, and it protects us every single day of our lives. Now, has anyone seen the aurora of recent events? Yes. So this is like a peak example of this protection from our magnetic field. We can get geomagnetical storms where we have plasma interacting with our upper atmosphere and jiggling along our magnetic field lines. And if we didn't have it, that radiation would be stripping away our atmosphere and eventually ending up on the ground. So there are two reasons why our Earth is special out of many, but they're the two main ones. Okay. I'm going to start this talk with what could have happened. So we're talking about before life even formed on the Earth, before the Earth even really existed, what could have happened in the universe? And there's a lot. So one way is that the universe just could have never formed, full stop, that's it. Could have happened, and I'm glad it didn't. There's a couple other ways. One is that our sun might not have formed in just the way that it had. So I'm going to break down a theory called double trouble or nemesis theory. So our sun is something called a G-type star. It's a main sequence star that burns hydrogen in its core. Our sun is fantastic. We love it because without it, we wouldn't be here. But there's a really decent theory that at some point our sun might have had a twin. It might have had another star in orbit with it in a binary system. And we call this star Nemesis. Whether it would be Nemesis or not, to be concluded. But why that would be so important is because if we look at our solar system today, this is obviously not to scale, but we have all of our beautiful planets in line. The way that our planets orbit around our solar system is really particular, and it's based on gravitational interaction and the fact that we can get semi-stable orbits based on distances to each other. And if we had another star in our system somewhere, it could have thrown all of this off balance, quite literally. Okay, so why do we theorize this? One theory is because our type of star, which is a G-type star, only makes up 7% of all of the stars in our galaxy. If you were to count all of the stars, we are the vast minority of stars. Most of them are a lot smaller than us. If you look at those 7% of stars, though, you find that 60% of them are either born with a twin or still have a twin partway through their life. So the majority have a twin. And it brings us back to questioning, well, if our sun is part of this group, there is a statistically significant chance that we would have had a twin at some point. And two things could have happened. One is that it was gravitationally unbounded and went off and is orbiting somewhere else. It might be a star that we see in the night sky today. That's kind of lovely. Or that it's still there. And you're probably on the same page of thought as me. It's most likely not still there because we don't see a large gravitational influence. We don't see another star like our own in the sky. So it was most likely broken off at some point. Okay, why is this important though? If we had a different system, if we had a two-body system, so our star and a different star, could be similar size, could be bigger or smaller. As our planets were trying to form, they might not have formed in the same orbits that they have, or they would have collided together. And so I'm going to show you one system. This one literally makes me a little bit queasy looking at it. It's a sextuple system. So all of these stars are somehow gravitationally bound to each other. And we have a couple of different systems happening. We've got a true binary system where they're orbiting around a central point. We've then got binaries orbiting around binaries. And then we've got this other system here, which is interacting with the other four stars. Now, in a system like this, if you were to live on a planet orbiting around any one of those stars, would you survive, do you think? Who reckons yes? Who reckons no? I think the no's have it. You most likely wouldn't, because your gravitational, your gravitational pull between the different systems would change dramatically over time. So there'd be sometimes where you're very close to a star, sometimes very, very far away from a star. Now, these are different types of stars which release different types of energy, but the most probable thing is that you kind of wobble in and out of these different energy zones. Essentially, how much energy are you getting from your sun? If you're not getting enough, you freeze, your water doesn't become liquid. You get too much, you become too hot. Has anyone seen the three-body problem? Heard of it? There's a book and then there's a Netflix show. Science is questionable, but it is a very good kind of representation of how difficult it would actually be to have a stable orbit and the fact that it's just physically not possible. And you can try mathematically and analytically solve a three-body problem. Try doing this. This would be insane. And you can't have a stable orbit. They always end up decaying and doing something interesting. So that's one thing that could have happened. Our sun could have still had a twin and Earth wouldn't have formed. Another thing that could have happened is that we might not have ever received our moon. Now, who knows how the moon was formed? Some people? This is my favorite thing. I think when I learnt this, it made me so happy. So our moon was once a planet, we theorize, called Theia. So our moon is really, really big. If you look at the mass of the moon and the size of the moon compared to our planet, it doesn't really fit in. If you look at Mercury and Venus and Mars, none of them have big moons. Mars has two little moons that were asteroids. One is going to fall into it, one is going to fall away from it. But none of them have moons as big as ours. Not until you get out, really, and you're looking at the gas giants, do you see moons even comparable in size and shape and composition. And so what happened? Because that's very strange. And we don't like coincidences in the universe. There's always some type of incredible science that can explain why we see things the way they are. So our moon. We think it was a planet potentially that we call Theia. It would have been a planet trying to form just like the Earth was in the very, very early universe, 4+ billion years ago. And they were all orbiting around the sun, condensing into their planet form. And what would have happened is Theia and the Earth would have collided at some point. Now, there's 4 different mechanisms for how we think that actually consolidated into the moon. One of the main theories is that throwback was flung off. Our Earth would have had beautiful rings for a short period of time, and because they were within something called the Roche limit, they would have condensed together and formed the moon. And it's excellent because we really like our moon. We think it's not only beautiful, we need it for light at night. There's a lot of species that rely on the moon to be able to do what they do, but we also need it for our tides. Now, Our tides are a combination of both tidal forces from our sun and from the moon. But the way that water transport works around the Earth, if we didn't have the moon, might have affected how life and nutrients formed all of those years ago. So it's very important. We might not have had that. Okay, so that's just one thing that could have happened. There's a whole heap more, including the fact that Jupiter might not have come too close to us in the early solar system. We think that Jupiter is a friend, not a foe. There's lots of different things that could have happened and thankfully did not. But what could still happen is the big question. And this is probably the one that keeps us up at night when we really think about all of the different things, because there's a lot. We could get hit by an asteroid. We could have a rogue gamma ray burst. We could have an alien invasion. I'm quite partial to this one. We could have a giant solar flare. They're probably not. We could have the simulation turn off. There's a theory that we might just be a simulation and one day they unplug us. All of them are terrifying to a certain degree. All of them are very unlikely to happen, which makes me very happy. But there's a lot of thought experiments that go into what would happen if we got hit by an asteroid that was just a fraction of the size of the dinosaur. What would happen if aliens tried to invade us, and what's the probability of that happening? You know, what would happen if we got hit by a very large CME from our sun? Probably wouldn't affect us here on the ground, but it could wipe out our infrastructure in space, which could then just have run-on effects for decades, depending on how crowded our space is. There is one thing I want to talk about today, though, that I think is probably the most fun out of all the thought experiments, because it's the most unknown, it's the most uncertain. And that is this beautiful thing here, which is a black hole. So I want to talk about the theory of what happens if a black hole were to eat the Earth. Has anyone thought of that before? Yeah, it's kind of natural. Once you learn about black holes, you become terrified of them because they're so mysterious and interesting. But I promise you, they're actually just big, gentle giants. They don't want anything to do with us, and we don't want anything to do with them. And we will live happily ever after, most likely. Okay, so black holes, friends or foes? We're going to break it down. Before we break down, should we be afraid though, we have to break down what is a black hole. So a black hole is this theoretical prediction of an infinite point in space and time where you've got a very dense point of space and time. So all matter is condensed into a single point. Einstein kind of first predicted this. So general theory of relativity, which was Einstein's 5 tensor equations from over 100 years ago, was able to mathematically describe how space and time would bend. You can then solve those tensor equations for a heap of different solutions, making some assumptions. And one of the solutions is that you get this. You get a black hole, an infinitely dense point that has an event horizon where nothing can escape. Its escape velocity is now bigger than the speed of light. And what I think is so interesting is Einstein himself was not a fan of this solution. He really didn't think that black holes could, one, exist, and two, that we would actually be able to find them, because just understanding what they are, you can't see them. You can only see their interaction with things around them, which is insanely hard to do. And 100 years ago, this thought was really, really perplexing. We do know now, though, that we do have lots of black holes. We've found many, many different types. We have stellar mass black holes and we have supermassive black holes. And we probably have something in between, but we don't know what yet. We're still investigating that. So I want to start with supermassive black holes, because I think if you had told Einstein this, he might have literally fallen off a chair. But they exist. We've found many of them in our universe. Okay. So this is our galaxy here. This is the Milky Way. You can see where approximately we think our sun sits there on a minor arm. Can anyone guess where the big black hole is in our galaxy? I know you all know. It's in the center. Yeah, exactly. If you were to zoom in, our big black hole would be dead bang in the center of our galactic bar. Now, this is what our black hole looks like when we actually take an image. An image is a very generous word. We're mapping the radio movements of material as it gets spun around that black hole. So this is called Sagittarius A star. It was first theorized and kind of confirmed back in 2002 when they were able to map a star moving around it, S2. They were able to say that star is moving at X velocity, at X distance, there has to be something very big in the middle. They weren't able to actually visually confirm that this is exactly what we thought it was, which was a supermassive black hole, until only a couple of years ago when we were able to get this image. So what we're seeing here is kind of the black hole, but not really. So in the center, we're seeing the black hole shadow, which is about 2 and a bit times actually bigger than the event horizon. We're then seeing all of this yellow and red light is material that's been sped up and flung around the black hole. It's in something called an accretion disk, and it is traveling at immense speeds, fractions of the speed of light. And we're seeing synchrotron radiation coming off that material. What's kind of amazing, though, is that this black hole is 4.1 million times the mass of our sun. It is enormous. And if you were to actually measure how big that event horizon is, it's 12 million kilometers, which sounds, again, enormous until you put it into perspective. You can actually fit this entire thing, including the accretion disk inside the orbit of Mercury, which is actually quite tiny. So it's very, very dense. It's very heavy and massive, but it doesn't take up a lot of space. It is also 25,000 light years away from us. So should we be afraid? No, we shouldn't be afraid, not of that one. So if we go back to this black hole, if we go back to this galaxy image, we can see a few different black holes actually. So we've got our big center one that's in the middle. We know that that is there for certain, a big supermassive black hole. We also think, and we theorize, that there are over 100 million black holes just scattered throughout our little galaxy by itself. 100 million of them on the minimum side is what we think exists out there. Now, that does sound like an absolutely enormous number, but if you put it into perspective that we think there's 400 billion stars in our galaxy, it's a tiny fraction are actually black holes. So what are the chances of one creeping up on us? Because unlike supermassive black holes, stellar mass black holes are really tiny, really, really tiny. So would we see one coming? No, probably not. So a stellar mass black hole is, for one that is about the mass of our sun, or a couple solar masses, 3 to 6 kilometers in radius of its event horizon. It's so tiny. They don't typically have accretion disks, not like our big black holes. They might have a very small one, but not one that's very bright optically for us to see. So would we see one coming? No, we physically would not see it coming, but we might see its effects. So if we had a black hole come a little bit too close to the Earth, say a light year or so away, what we would start to see is that we'd get more asteroids and more comets coming in our direction, which again, ask the dinosaurs, not a great time. We don't want to increase our risk of anything hitting the Earth. We already have potentially hazardous asteroids that come quite close. Any external gravitational force can increase the risk of them and others hitting us. So we might pick up on it that way. This would make a great sci-fi. If anyone's listening, please write this, because I would love a movie like this. All of a sudden you're getting asteroids and comets galore and you can't know why. It's a black hole. The other thing that can happen is that if it were to come within our solar system, so if it were to creep within, say, the orbit of Jupiter, so get pretty close to us, it could actually gravitationally push us towards the sun. And I don't think I have to tell you that that's not a good thing. We would not enjoy that very much at all. We'd probably boil. It could also pull us away from the sun, just depending on where exactly it is and mainly where Jupiter is at any given time. It will change our orbit dramatically. So we'd either freeze or boil, and that's not great, but would we ever be eaten by the black hole? Chances are really slim, and I don't know why this makes me sad, and maybe I need to talk to somebody about that, but I think it would be brilliant if that is the way that the Earth is going to go, to actually fall into a black hole, because the whole trip would be incredible and insane. Does anyone know what happens when you fall into a black hole? Spaghettification, yeah. So as you get closer and closer to the event horizon, your time starts to dilate really, really significantly. So you or us falling into the black hole, we'd be looking back at the universe and we would see the universe unfold before our eyes. We'd see 1,000 supernovae, we'd see Andromeda merge with the Milky Way. We'd be treated to this like spectacular show as we were watching time unfold. We would be being sucked in and our particles were being ripped apart. But if we could survive that, we'd see a show. If somebody was watching us, we'd look like we were stuck on the surface of the black hole for infinity, which would not be great. Once you pass the event horizon, then that's when spaghettification really takes place and everything gets stretched and pulled. All of your particles would break down to their subatomic particles and you'd all be condensed into one happy family at the center of the black hole. So the chances of that happening, though, are so extraordinarily slim. I don't think we have to worry, though. Again, if anyone would like to make a movie about it, I welcome it. Okay. So what will happen? There's a heap of things that could happen, but will absolutely happen. No ifs or buts. This is it. The world will end. That's two things. One is that our galaxy is going to merge with the Andromeda galaxy, and the other is that our sun is going to die. Both are epic. Both are happening on very similar timescales, and if we were to survive, both would be spectacular. So we're going to dive into death of the sun tonight, because that really is the end of our Earth. And it's this humbling reminder that the Earth itself is very deeply tied to the existence of our sun. We wouldn't exist if our sun hadn't formed, because we are the leftover material that didn't form into our protostar. And we won't exist once our sun eventually dies. So how will that happen? Right. Our sun is roughly 4.6 billion years old. So as I said before, it's this G-type main sequence star, which just means she's middle-aged. She burns hydrogen in its core, and it will live for approximately another 4 to 5 billion years old. It's one of these stars that actually has a really fantastic lifespan. We've kind of got two ends on the spectrum. We've got some stars that die very, very quickly, tens of millions of years, and that's it. They're gone. Life forming around one of them is probably exceptionally slim. So it makes sense why we're not around one of them. We then have stars that are red dwarfs, so very, very tiny, a quarter of the size or so of our sun, and they will burn their fuel for an extremely long amount of time, hundreds of billions of years, if not trillions. But they don't release a lot of energy, and so it's quite hard for a planet to be close enough to have liquid water. They also flare a lot as well, which is probably not great for life on long term. So our sun is one of these stars that's kind of literally in the middle. I'm very happy about it. So this is what I was talking about before. So we have our big blue stars which die fast, our little red stars which live forever, and then our sun. What is cool about this type of plot, this is a Hertzsprung-Russell diagram or an HR diagram, is that you can track the evolution of stars. And so our sun is currently in the middle. It will go up and become a red giant, and then it will fall right back down and become a white dwarf. So a red giant will happen when it starts to burn helium in its core, and we get a pressure pushing outwards, and our star will get bigger and bigger and bigger. As that happens, its surface is moving closer and closer and closer to the Earth. Eventually, though, it will no longer be able to hold everything in. It's kind of gravitationally unbound, and the remnants will just breeze away, and you'll be left with the very dense core that will cool down over a long period of time, and that's the white dwarf. Okay, so we talked about the Goldilocks zone a little bit at the beginning, this idea of a region where water can be in all three states. Mainly it can be liquid very easily. If you move a planet too close to its star, you end up getting somewhere that's too hot for liquid water to exist. Same thing, if you move it away from the star, it becomes too cold. Now, you don't actually have to move the planet for this to be true. You can also just move the star closer to the planet. So as our sun expands and gets bigger and bigger and bigger, it's going to get really hot. It's going to increase its surface temperature about 1% every 100 million years. I'll have to double check that. But essentially, our math is that in about 1 billion years, so that's a good amount of time, it will be far too hot for our oceans to actually survive as they are today. So we've got about 1 billion years to get ourselves together as a civilization and find Earth 2.0 and hopefully treat that one very kindly. We then get to a point where not only liquid water starts to boil away, but the surface starts to get hit with more and more radiation. Our atmosphere and our magnetic field cannot protect us from all of it, and it will become a scorched Earth situation. Not great. We then have the very, very real possibility that our sun is going to expand so much that it will actually engulf the Earth and just eat it, for lack of a better word, entirely. That will be the certain death of our Earth. The good news is that we're going to be left with something like this. So this is a planetary nebula, and you can actually see the death of a star that once was in these outer rings. You can see some of the hydrogen and the helium and different elements in different colors. In the center, if we could see it, we would see a white dwarf. And then somewhere in amongst here is probably the remnants of several planets that once orbited this beautiful system. And I don't know about you, this could just be the existentialist in me, but I like to really think about the fact that one day there's probably going to be life out there in the universe that is looking at us as one of these, that is looking at our planetary nebula and saying, isn't that pretty? And thinking about what would have been there before, without knowing that we were actually there. Everything we've ever known, unless we get off the planet, which, take your bets if that's likely or not likely, but everything we've ever known up until right now in history is within this type of nebula when our sun dies. And I think that's a good way to end, quite literally. I will plug, if you want to learn about all of the other ways that the universe could kill us, but probably won't, you can buy my book and use code ASV10 to save some dollars. These are all signed copies, and I have a few here tonight if anyone would like to get one tonight. But thank you very much for your time.
I'm going to ask if we have any questions, but before we do, I have a question. When you were talking about black holes and spaghettification, and you mentioned that if you at that event horizon, you become spaghettified. But if someone's watching you,
You look like yourself.
and you never get spaghettified, is that like the Schrodinger's black hole?
It could be.
Yeah. So you see yourself it happens straight away for you, basically. But the person watching you,
They
watch you forever. So technically, you never die.
It's kind of nice.
Yeah, it's poetic, isn't it? Do we have any questions for Sarah? Oh, we have a couple. All right, so we'll start here, and then I'll have to run the mic back up.
I hadn't heard the spaghettification one before, but it sounds interesting from the point of view for cowards in a simulation.
Oh, yeah, there's a fantastic one by NASA. So there's a simulation of what you would see and what an observer would see of the spaghettification. Yeah, it's fantastic. I can share it with Mark to share with you guys, but it's really trippy. Yes, just going to show you, and then It is excellent, though.
We have another question. Yep, I'm going to pass you the mic.
My question's just in regards to the micro black holes. There is a theory that says that micro black holes just roam wherever we look. Do you think maybe... Okay, sorry. Do you think that we will, like I know you've said in the talk that we wouldn't be able to identify them, but do you think there's actually more than what they think of the micro black holes?
That's a good question. So those are the stellar mass black holes, which we estimate the number of, and they are formed when big stars die. So big stars have to die for those black holes to form. There's also the idea of either very small low mass black holes that exist based on other physics, or primordial black holes, which are, again, very, very small, that could be left over from the beginning of the universe, both of which would be so tiny that gravitationally they're quite hard to find. But you could try and find them using things like microlensing, but it would be quite hard. So we do look for microlensing of more stellar mass black holes, and then trying to find primordial mass or very small mass black holes. So they could, in theory, this is one theory for what made up dark matter, was these machos. And it looks like it's probably not the answer, just based on how often we've looked and how little we've found so far, which is a good thing for us. It means that there's not black holes roaming everywhere, which is great. Yeah.
Do we have any other questions? Well, There's no questions online, but a lot of thank yous, great talks, and wonderful presentations, Sarah. So, Sarah, thank you very much for your talk tonight. And I think the black hole thing you were talking about, like the poeticness of falling into a black hole, and that's the way it all ends, was the topic of discussion at the Q&A dinner of what would be one of the most amazing things to see in the universe. And in the end, the whole panel agreed that falling into a black hole would be a great thing to see if you could survive it. We're now getting ready for Bill, who promised he would throw my laptop off but didn't. I'm disappointed.
Oh, I put it down very gently.
Yeah.
Turn me down.
We're going to hand it over to Bill now, who's going to give us a talk on what's up for November, December. What's in the sky? What is in the sky, Bill? What's exciting that's coming up?
Well, hopefully there's no black holes nearby.
No black holes? No micro black holes?
Yeah, by the way, Sarah, I didn't have a question for you, but I did have an answer. The question was will we end up the same way as the dinosaurs? And the answer is no.
Why is the answer no?
Because we won't even leave bones. Right.
I don't know if that's a dad joke or not.
No, it's just this is supposed to be threatening.
Ooh.
It's a threat. I'm
going to hand it
I hear
over.
they're very effective.
Yeah? All right.
Never been very good at them. Like Slutty Bardfast.
All right, I'm going to hand it over to Bill now.
Oh. Hang on. I haven't got my laser pointer. Hang on. I've just got to find it. Suddenly realise I'm naked without my laser pointer. Arrgh. Damn it. Oh, I must have left it at home. I will. I was hopefully going to use it tonight, but that's okay. That's okay. Okay, today is not Wednesday. I think the turnout shows that that's a little bit off the beaten track. But so it's the charts I'm about to produce are for the 13th of November. But we're talking about what's in the sky between late November, which that is now, and early, like mid-December 2024. So first of all, tonight we are on the lands of the Bunyurong and the Warrung people of the Kulin Nation. The Bunyurong is the people who were south of the Yarra, so you're quite correct. You were on Wurundjeri country. I'm going to be speaking about, as usual, the general conditions of this time of the year. What's in the sky, including the moon, the planets, some orientation stars, constellations, the occasional planet. Then I'm going to go through the list of suggested targets for tonight, visual and photographic, and then talk about tomorrow morning, 5 a.m., followed by a short list of things to look for this month. Ooh, what happened there? Looks okay here. You've got a... Yay. All right. I'm still going to have to do this. General conditions this time of year. It appeared there for a second. Okay. We're losing our darkness quickly now. The current daylight length is around about 14 hours, which means that that opportunities for observing are getting short. The summer solstice is at Christmas, but most of the changes happen around the equinoxes. So most of the growth of light we've had already. Sunset is about just after 8 p.m. tonight. Don't bother looking for anything until 9 o'clock. Next month, it's going to be about 8:40. So we're going to lose about half an hour of observing time by the next month. Sunrise is about 6 a.m. Again, stop observing at about 5. Next month, we're going to lose about 10 minutes over the next month because it's slightly, it's not quite symmetrical. Ooh. It's like, oh dear. We are going backwards. What is going on? Oh, there we go. Oh, I'm getting ahead of myself. Right. Seeing conditions might start to deteriorate now. Now, the Bureau of Meteorology, they come up with predictions. They call them long-term, which is like 3 months. Their maximum temperatures are likely to be around about normal, but unusually high minimum temperatures are very likely for much of Northern and Eastern Australia, that's us. So our minimum temperatures are likely to be a bit on the warm side. Now, that's not great for astronomers. Now, this is where I have to use this machine. Oh, look, there you go. Okay, so this is the mean, minimum, maximum and minimum. These are the maximums, and these are the minimum temperatures for Melbourne and for LMDSS, close enough to Redstale. So you'll notice that in winter, Redstale, the LMDSS gets an average minimum temperature of around about 3 degrees, which is nice and chilly. That's good for astronomy, not great for the astronomers, but it's good for astronomy. By Christmas, you'll notice that it's actually getting up to around about 10. So we've actually got 7 degrees, and in February we get even more. So in summer, the seeing conditions are not the best, shall we say, particularly for the planetary astronomers who are looking at really massive magnification, because the sun will just, the moon or whatever it is they're looking at, will just do this nice little shimmery dance, which is, look, on some nights, it's God's way of telling you not to bother with the scope. So now the other thing is this business about the jet stream. Now, if any of the planetary people want to explain the jet stream to me, I would love it, because I did a little bit of research on it the last month, and oh my goodness, it's complicated. So yeah, I'll leave that to somebody else. Poor old young astronomers have been squashed to the very bottom of the thing today. Young astronomers, why do planets move in the sky? Do they always move in the same way, and why? And why not? Now, I realise that the third question has answered the second question, but that's all about understanding. And why I'm asking this, just wait a second. This month's moon. Now, this is one of Kate's photographs. I put it on appeal for her photographs, and I thought this was just a corker. Don't you love that cloud? And now, this was taken up at Sea Lake the other day. Oh, thanks. And up there is Venus, and there's the moon with its ashen light, but you can hardly see it. But just around about there is Mercury. Mercury put on a great show for us on the weekend. It was just fantastic. Anyway, getting back to the moon. The full moon is on Saturday the 16th of November. It's across to the north. I'm going to have to get my glasses for this, I'm afraid. It's across to the north for on the 12th. So it's going to be low in the sky over the next week or two. It's a supermoon because we are close-ish to the perigee. I'm suddenly talking very loud. It rises at sunset and sets at sunrise, which means that it's poor viewing due to direct light. There's no point in looking at a full moon. It's just boring. You can view it all night and over the following week as a waning gibbous moon. Now, the last quarter is on Saturday the 23rd. It crosses to the south on the 25th, so it's going to start to get high in the sky. So you'll be looking at a moon fairly high. It rises at midnight, sets at noon, and over the following week, it's going to be a waning crescent. It's going to get thinner and harder to see as it approaches the sun, and it's going to start looking like that. You view it in the morning, then later in this week in the early afternoon. The apogee is the 26th. Now, from here on, I don't know if you remember the wobbly lines that I had going a couple of months ago, which I seem to have dropped because they're complicated. However, from here on, for at least a few months, the distance and the phase lines are out of sync, so we don't get supermoons and mini-moons for a while. The new moon, however, is on Sunday, the 1st of December. It's not close to perigee or apogee, so I'm calling it a meh moon. It rises at sunrise, and it sets at sunset. Obviously, that's what new moons do. It's going to be a waxing crescent, looking like that again. It's very thin. We will be able to see it a few days after sunset, as this was. The first quarter is on Monday, the 9th of December. It rises at noon, sets at midnight, which is the best time for viewing the moon. And that's the reason why a lot of star parties are done at the first quarter. It crosses to the north again at about the same time. So it'll rise bang on the east, and then it'll go low in the sky for the next fortnight. And the perigee is on the 14th, which is after next meeting. Okay, so moving to the planets. over the next month. This is from the ASV yearbook. Mercury is an evening object now, as you could see from the previous picture. It's in the west. It's out of the twilight and close to the greatest elongation. The greatest elongation is on the 16th. And look, you've got to go and see Mercury now. It's hard to see at the best times. This is the best time to see it. Sets at about 10 p.m. It's close to Antares, and it's magnitude -0.3, so which means it's bright as. Speaking of bright, Venus is even brighter. It's -4. It's an evening object further up, as you can see from the photograph. It sets at about 11:30, but Venus is dull as dishwater. The only interesting thing that Venus does is goes at a crescent, and it's gibbous now. So boring. So, okay. So I'm allowed to be harsh. Venus doesn't care. Mars is finally moving at about the same rate as the other planets. It rises at about 1:30. It's going to be stationary on December the 8th, and then it's going to move into retrograde. The opposition is mid-January 2025, so this is the time when Mars does its thing. It does it every 18 months or so, and so Mars opposition is when you want to be looking at it. It's great. Jupiter rises about 10:20. It's going to be consistently earlier until opposition, which is in December. It will continue to brighten noticeably, although it's already very bright, and it's, again, not far from Aldebaran. Saturn is almost past its prime now. It sets at about 3:30 a.m. Retrograde ends it ended on November the 16th. Ends. There's another week. The rings are closing, which is going to be very interesting. That's happening in March 2025. So it's still in a good position for evening viewing, but it is going to get less bright. Now, it is the star of the show at the moment, particularly for the tours that are happening right now. I'm supposed to be over there. Uranus, the opposition is November the 17th. So it rises at sunset and sets at sunrise. So it's a good all-night viewing if you've got the right telescope. You're going to need a lot of magnification and probably aperture as well. It's ahead of Jupiter. It's not very far from the Pleiades. You'll probably see it later. Neptune is rising in the afternoon. It sets just before 4 a.m. It's most of the night. The retrograde ends on December the 8th, which means it's going to be dimming, although for Neptune and the outer planets, that brightening dimming cycle is fairly subtle. Pluto is rising during the day. It sets about 1:30 a.m., so it's now an evening object, and the opportunities for viewing are getting a little bit thin, but Pluto is Pluto. It's hard to find. Now, quick tangent. What's retrograde? Now, astronomers tend to look at the sky night after night, and the ancient astronomers certainly did. So background stars move night over night. They move from east to west. And now their right ascension coordinates remain fixed because, they're stars. That's what they do, or moving is something that they don't do. Of course, there's precession, there's other things, but this is called sidereal motion. However, planets, generally speaking, they move in what we call prograde motion. That's most of the time. And they move slower towards the west than the background stars. So that means the stars are overtaking the planet. So when plotted against the stars, the planet appears to move eastwards. It's lagging behind. Their RA coordinates increase each day. However, during retrograde motion, that's about certainly a lot less than half the time, depending on which planet it is. The planets move faster towards the west than their background stars, which means the planets overtake the stars. Now, against the stars, the planet appears to move westwards, and the RA coordinate decreases day after day. Now, the ancient astronomers looked at that, and it turned their brains into a pretzel. They could not, for the life of them, figure out what they're doing. Now, here is Mars. Can we turn the lights off again? Because no? Yeah, yes, we can. Okay. I was just looking straight at that thing. I can't see anything. But this is what Mars is going to be doing over the next few months. As you can see, it does this big loop in the sky. So I'm going to find a thing that works. That one. Okay, so here, Mars is around about sort of here-ish now. By the way, this is Castor and Pollux here, so that'll give you an idea of where it is. So Mars is about here. It's in prograde, and when it comes to here, this is the 8th of December, and this is when it appears to be stationary. It stops and starts going back the other way. And then it moves in prograde. It's going to move back along here. And then when it gets to about here, this is opposition on the 16th of January. This is when it's closest and brightest. And this is where all the planetary astronomers lose their minds. And here is when it stops and it appears stationary again, and retrograde is finished, and it keeps on going back towards F in there. So that's what Mars is going to be doing over the next few months. So retrograde is, I might have said this before, but retrograde motion is something that really stimulated the birth of modern science, because people looked at it and went, that breaks what I always thought planets were and what they did. And then they had to start reappraising their theories and stuff. So philosophy started. Okay, so let's get orientated for this for 10 p.m. The Southern Cross is nearly at 6 o'clock. You'll notice that it's about as far down as it gets, very, very low. So normally it's in the trees. Sometimes it's hard to find it. Get rid of that. Scorpius has also mostly set. These are my three road signs: the Crux, Scorpius, and Orion. So Orion is it's the first time we've seen Orion this year at 10 p.m. So welcome, Orion. So now our orientation stars, it's a little bit like a cricket commentary here. I've got three people on the inner field and three people on the outfield. We've got Achernar, which is slightly southeast of the zenith, up there. There's definitely a donut warning there for people with Dobsonians. Fomalhaut is slightly west of the zenith. It's past the donut, so I don't have to worry too much about that. Canopus is lowish in the southeast, and that was easy one to find at Sea Lake last weekend. Altair is low on the west-northwest horizon, so that's just about set. Sirius is rising on the east-southeast horizon, and Aldebaran is low in the east-northeast horizon. So these last two are coming into play. Altair is on its way out. It's getting subbed. Saturn, this is not specifically about stars. Saturn is past the meridian, and it's very high. Venus is, you can just about hear it in the west, and Mercury has, well, Mercury, that's Mercury just there, just about gone. So it sets at 10. Right, visual targets for this evening. This is again for 10 p.m. today, although you're not going to be seeing much because it's cloudy outside. Mercury, you're going to have to be quick because it's about to set. Then Venus is there, but like I said before, dull as dishwater. Saturn is still the star, although it's a planet, and that's past the meridian. Beta Tuc is a triple, and that's right on the meridian at the moment. It's not quite donut. It's not too close to the zenith for you to be able to have difficulty seeing. 47 Tuc is fairly close, and that's going to be the sort of thing you're going to need to see from a dark sky site, because it's a little hard to see from the city, sorry. P. Eridani is cat's eyes, which is a beautiful thing. You must see that if you can. It's very easy to find. It's right next to Achernar. Get Achernar in your finder scope and you can see P. Eridani in the same view. Theta Eridani is another double. It's a little bit further out. It's they call it Acamar, not to be confused with Acamar. And now if you're again in the dark sky site, LMDSS, the Tarantula Nebula is very easy to see. You won't need much in the way of magnification to be able to see it. It's very nice. Alpha Capricorni is an optical double. It's not actually in orbit around each other, but and it's also very wide. It's to be honest not my favourite, but it's not dramatically interesting to see. But I'm running it down. So it's a good little target to spot. The Andromeda Galaxy is something that everybody always wants to see, not because it's just going to scarily eat us, but it's safely in the north. It's got a very, very short viewing season, Andromeda. You only get about 3 months of decent viewing. So if you want to see it, you're going to need to get out, hopefully at the top of a mountain, certainly away from trees because it's very low. Sea Lake was a brilliant place to see it from, by the way, except for the clouds that were on the horizon. That's okay. Pleiades, always everyone's favourite, M45. It's on the way up, very wide open cluster. You're going to need a very, very long eyepiece to be able to get all of that in. Gamma Ariatis, last one I think, is Mesatum. That's another double, which is very worth seeing. So okay, that's all of that. So now the photographic targets. This is when the visual people all walk out of the room, and the astrophotographers, well, they've been hiding in the back anyway. So because astrophotographers are all, without exception, boring people. So I can say that because I'm an astrophotographer. Okay, so we've got now these images. By the way, I've stolen shamelessly from the ASV Facebook page. These are the people who have shared the photographs with ASV members, and that's exactly what I'm doing right now. So, String of Pearl Galaxy, NGC 55, donut warning, it's dead straight up. Nice photograph from Oliver White, thank you. The Southern Pinwheel Galaxy, again, a donut warning. This is NGC 300, and I think this is Diego's photograph, so it's probably several years old. Triangulum Galaxy, does anybody know somebody called Lee Green? Never heard of him? Okay. All right. That was, I think this is a couple of years old as well, Lee, isn't it? Uh-huh. Okay. Well, in that case, you're surprised you don't get trees in it because this is another one which is fairly low. Andromeda Galaxy, even lower. Wyatt got this from LMDSS, I believe it was, just the other day. So this is newly on the website. Sorry? Oh, stop. This is one of Russell's. It's NGC 1365 and some Fornax cluster. This is actually one from last month as well, but I didn't get to talk about it very much. Don't you think the colours on that are amazing? So Russell's very good at this. It's also called the Propeller Galaxy for fairly obvious reasons. Large Magellanic Cloud and the Tarantula Nebula. The Tarantula is that mess in there. So you can easily see that with binoculars, and as you can see, this is a 50mm. I cropped it slightly, but this is a 50mm camera shot that I got from Sea Lake last weekend. Helix Nebula. This is Gerald's photograph, and I think it's an HOO photograph, but yeah, it's very easily got at the moment, and it's just past the meridian. Pleiades. One of my presentations is not complete without an Eddie Pang photograph. Look at that. There's a lot of stuff around there. Sculptor Galaxy. This is a remote dome image. Sculptor Galaxy is very nice, and it's approaching the meridian now. Finally, 47 Tuck and the Small Magellanic Cloud. This is a Jeff Healy photograph, so that's always well worth getting to. I think that's it for photographic targets. So tomorrow morning, I'll just rattle through this really quickly because I'm getting a bit long. Get rid of that. Southern Cross is about 9 o'clock. You can see it's sort of moved from there all the way up to there in 7 or 8 hours. Yes, get rid of that. Orion has passed the meridian. The Scorpius is gone, and the planets are dispersing. We had a nice little cluster of them a few months ago. Saturn and Neptune have gone. They've now set. Uranus is still not far from the Pleiades. Jupiter is past the meridian, and Mars is starting to become the hero. It's coming up towards opposition. It's getting brighter, and it's going to be awesome. Okay, so final notes. These are random observations. 16th of November, Saturn retrograde ends. So it'll be stopped. Also the same day, Mercury is the greatest elongation, so that's your best time for viewing. 17th of November, the next day, Uranus is opposition, and yes, will we get a good look at Uranus? 26th of November, Mercury starts its retrograde. Mercury retrograde is weird, so and it's hardly matters. 30th of November is the ASV Starbecue, so everybody will be here, of course. Actually, no, they're up at LMDSS. The 6th of December, Mercury disappears underneath the sun, Now, okay. On the 8th of December, expect astrologers to lose their fucking minds. Strap in. Jupiter opposition. Mars is stationary moving into retrograde. Neptune is stationary moving out of retrograde. Saturn occults the moon on that day. There's also a lunar X during the day at 1:36 in the morning, in the evening, so it's going to be like in the afternoon. And it's my wife's birthday. So astrologers are just going to go absolutely nuts. Please make friends with an astrologer. They are interesting people to talk to, but don't. Yeah. So there we go. Thank you. So we're done.
Probably not now, yeah. Thank you, Bill. A couple of clarifications for you.
Yes.
None. But I wanted to thank you for your amazing presentation last month as well.
Oh,
it was brilliant.
Yeah, look, it's amazing. I hardly recognised myself.
I know, you were so very different. And you even used some of my photos, which I was very impressed with. So thank you for doing that.
Well, I'd never do that. By the way, these I am the same person as Mark because no one has ever seen us in the same room together.
Shh, don't tell anyone. No one wants to admit to that.
No, nobody wants to admit Bill.
Thank you for pointing out the star party on the 30th of November, which coincides with New Moon, which is why it's on the 30th of November up at the LMDSS.
Yes.
Tickets are on sale now. Book. We have family passes now for non-members, and all kids come and get show bags this year. Thank you, Kelly, for putting those together. Wonderful. So again, I want to thank Sarah for coming tonight. Thank Bill Stant, the Telescope Gent, for another amazing What's in the Sky, which I will chop up in the next day or two and put on the YouTube as its own little thing as well. And thank everybody for coming tonight and for everyone who has watched at home. We will see you in December on the 11th for another Astro Talk, for the Christmas Astro Talk.
It's a Wednesday.
Come one, come all. It is a Wednesday, not a Monday. It will be a Wednesday. Come one, come all. We'll have a lovely gathering, Christmas gathering. Come and hang around and have some drinks and nibbles afterwards as well. We'll see you then.